So this lecture will cover the basics of how a mass spectrometer instrument works. So what's going on inside the box. So for a mass spectrometer, it basically has three pieces to it. Has what's called an ionizer, a mass. So the sample goes initially to the ionizer, and then it goes to the mass analyzer, and then it goes to a detector. And there can be other components to a mass spec, but that's the basics of what every mass spectrometer has to have. So there's different ionization methods. You have what are called electron impact, mass spectrometers. So ionization meaning you introduce a neutral molecule and you have to get the molecule charged before, in the very first step in the mass spectrometry experiment. So you got to go from neutral to charged. If the molecule is not charged, then it's not going to go through the instrument. Or you can have chemical ionization methods. You can have desorption methods to get the molecule charged. So what's known as field desorption ionization, or you can have fast atom bombardment, or FAB. So you can do FAB mass spectroscopy. Plasma, there's all kinds of different ones. Desorption. Laser desorption. Electrospray. So ESI, right. So A&M Commerce has an electrospray instrument, and we also have the electron impact, and so we're going to talk about the electron impact in more detail in just a minute. In terms of mass analyzers, there's different mass analyzers that you can have in a mass spectrometer. You can have what's known as a mass magnetic sector, and we're going to talk about that one in just a minute. A quadrupole. So we have several mass spectrometers in the chemistry department at A&M Commerce. We have some with magnetic sector. The ESI that we have has a quadrupole on it. You can have time of flight mass analyzer, ion trap, tandem mass spec. So there's basically all kinds of different mass spectrometers that you can build depending on which component you have. Okay, so let's basically go through how an electron impact. So electron impact, so this is the ionization method that it's going to have, and then it's going to have a magnetic sector mass analyzer in it. So this would be where the electron impact is at, in the ionization chamber, and then this would be the magnetic sector. So we'll go through how that instrument works. Okay, so if we take as a sample, let's take neon gas from nature. So neon's got 10 electrons in it. So what you do is take a syringe, drop some neon gas, and inject it into the mass spectrometer, and it first goes into an ionization chamber. So now we have our neon in the ionization chamber, and then so this is an electron impact ionization method. So that's exactly what it means. We're going to take very high energy electrons and we're going to impact them with a neon sample, and basically what this is going to do is going to knock going to knock an electron off of the sample. So neon initially had 10 protons, 10 electrons. You knock an electron off, now it has 10 protons, 9 electrons, so it's charged. And furthermore, if it had 10 electrons, all of the electrons were originally paired, right? Because this is 1s2, 2s2, 2p6. So all the electrons are paired. Now it's 1s2, 2s2, 2p5. So one of those electrons in one of the p orbitals does not have a pair. So anything with an unpaired electron is called a radical. And furthermore, it's charged. It's positively charged now because it has more protons than electrons, so it's a cation, so this is a radical cation. So in any mass spec, you have to get the sample charged, either positively charged or negatively charged in the first step, otherwise you can't do a mass spec analysis on it. And that's because of the next step. So the next step, what you do is you apply an electric field. And the purpose of the electric field to get the ion moving really fast. Not speed of light fast, but fast. So since it's charged and you put anything that's charged in an electric field, then through mutual attractions or repulsions, it's going to get the thing moving really fast. So now we have a neon plus cation moving fast. And then we're going to put it through a magnetic field. So one point to recognize here, so all moving charges have an electric field, and all electric fields have their own magnetic field. So this moving neon cation basically is like a tiny magnet. It's got its own magnetic field. So what happens if you put something that's has magnetic properties in the presence of another magnet, then that will deflect the path of the particle. And so in the instrument, then what you have set up is basically a wall with a tiny slit in it. And if the particle transverses the right path, then it goes through the slit and hits the detector. And then basically you can count the number of particles hitting the detector in a given amount of time. And if the particle does not transverse the right path, then it slams into the wall and is obliterated. So it may not be deflected enough, or it may be deflected too much, and then it hits the wall. Only if it transverses the right path will it hit the detector. So that's the purpose of the magnetic field, is to deflect the path of the particle, to make the path bend, and try to direct it through that tiny slit to hit a detector. Okay, so then what you do is you get a signal coming out of this instrument now because it's hitting the detector. And so what you do is plot on the vertical axis the intensity of the signal. So basically you can just count the number of particles hitting the detector in a given amount of time. And on the horizontal axis, you plot what's called the mass to charge ratio. So if the charge is +1, then this is mass. If the charge of the particle is +2, then it's half the mass. And so there are things that you can do to figure out what the charge of the particle is. So if we were doing this for neon gas, then we see 3 different signals. Why 3 different signals? Because neon comes as 3 isotopes as nature. And if you remember what the difference in isotopes is, they have different numbers of neutrons in the nucleus of the atom, so therefore they have different mass. And this is going to separate things out based on mass. So neon 20 has the lightest mass. It's going to come out, well, it's going to show up first. Neon 21 has a higher mass, and neon 22 has a higher mass. Okay, so how does this magnetic sector work? So if we go through this in a little bit more detail. So we have neon cations going through our instrument, but I like to use this analogy. Well, what if you had a NASCAR, an 18-wheeler, and a remote control car, and you get them going all the same speed? Well, so what is one thing that they have in difference is their mass. Okay, so let's say the NASCAR transverses the path and hits the detector. So they're all going the same speed, so what would you expect to happen to the 18-wheeler? So it has a heavier mass, so what would you expect? If you were driving the 18-wheeler and you got it going really fast and you put it through a corner, if the NASCAR, so let's assume everything can keep traction and not flip over, then what would you expect to happen to the 18-wheeler? Well, because of how massive it is, it's going to tend to want to keep going on a straight line and it's going to hit the wall. And the remote control car, conversely, does not have much mass, so it's going to be deflected too much and it's going to hit the wall. And only the NASCAR would hit the detector. Well, what if you wanted the 18-wheeler to hit the detector? So if you were driving the 18-wheeler and you wanted to make the corner, what would you do? Well, you could slow it down. So let's take this and slow it down. And then if it's going slower, then it will have a greater chance of hitting the detector. That would be one thing. You could slow it down, or you could increase the magnetic field. So if you increase the magnetic field, its path would be deflected more, and then it could hit the detector. And if you're driving the remote control car and you wanted it to hit the detector, then what you would need to do is you would need to speed it up to give it more forward momentum, so its path would not be deflected as much, or you could change the magnetic field, drop the magnetic field so its path is not deflected as much. Right, so that's basically what you do in a mass spectrometer with a magnetic sector mass analyzer, is you apply a magnetic field to deflect the path of the particle, but you can change the strength of the magnetic field. And you apply electric field to get the particle moving fast, but you can always drop the electric field to get the particle moving slower, or you can increase the electric field to get the particle moving faster. So that would be how you can get everything to hit the detector at some point, by changing the magnetic field or the electric field that's applied. And so another thing that you can change here is you can change the width of the slit. And that would be one way that you can change resolution. So if you make that slit smaller, then things that have slightly off mass won't hit the detector. But the downside of that is as you increase the resolution, the number of particles hitting the detector is going to decrease, so you're going to drop the sensitivity. So you're not going to see as much signal anymore. Okay, so let's go through just a little bit about how the math works. I'm not going to ask you to do this math, but just so that you understand how the mass spectrometer works a little bit better. So the magnetic deflectant force is given by this formula BZV, where B is magnetic field, Z is charge, and V is velocity. And that is equal to the mass times the velocity of the particle divided by the radius that the particle is transversing. So if we take that and then solve for velocity, so solve for V, so the two V's can cancel each other out to simplify the equation a little bit. And then if we rearrange that equation to solve for V, velocity, then velocity is equal to the magnetic field times the charge times the radius divided by the mass of the particle. And then another equation from physics, the kinetic energy of a particle is mass times velocity squared divided by 2. And that is also equal to charge times voltage. So now it gets a little bit confusing because we have two symbols V, one is representing voltage and one is representing velocity, so I've tried to keep voltage in purple so it's less confusing. So if we now take this equation ZV, charge times voltage, and substitute, so we solve for velocity here. So let's take that and plug it into this equation, mv squared over 2. So then so charge times voltage is equal to mass, and plug in velocity and square it, divided by 2. And then if we square everything, and then the mass, one of the masses will cancel out, so that will simplify the equation to this. And then if we take this equation and rearrange it so that we have mass on top and charge on bottom, so the mass to charge ratio, which is what's plotted on the horizontal axis of a mass spectrometer output. So the mass to charge ratio is equal to the magnetic field strength squared times the radius squared. You know the magnetic field strength and you can vary that. You know the radius, you can't vary that. And you know the voltage, and you can vary that. So since you know the magnetic field, you know the radius, and you know the voltage that you apply, then you can calculate the mass to charge ratio of whatever particle is hitting the detector. And you can make everything hit the detector because you can change the magnetic field and you can change the voltage. Okay, so if we look at the mass spec for neon gas in a little bit more detail, so we get 3 peaks, and the mass of the first peak, neon 20, is 19.9992 AMU, or grams per mole. Neon 21 has a mass of 20.994 grams per mole, or AMU, and neon 22 has a mass of 21.991 grams per mole. So these have a difference in mass of 1. So you could use a low-res mass spec to distinguish between these 3 isotopes because the mass difference is so large. So then from this data, how would you use it to calculate how much of each one you have? So what you can do is you can tell the instrument to take this area and chop that area off and integrate it. So we'll call that area 1, and tell the instrument to measure the area under this curve. So we'll call that area 2, and measure the area under this curve, and we'll call that area 3. So then the percentage, so we said this is neon 20, neon 21, neon 22. So the fractional abundance of neon 20 can be calculated by taking area 1 divided by area 1 plus area 2 plus area 3, the total area. Okay, so if you tell the software can do this for you. So if you tell the software to measure those areas and take the ratio, then it'll tell you for neon 20 it's 0.9051. So neon 20 in nature is 90.51%. And then for neon 21, you would take area 2 divided by the total area. So the amount of neon 21 in nature is 0.0027 or 0.27%. And neon 22, you would take area 3 divided by the total area. And again, the software does all of this for you. So 9.22% neon 22 in nature. Okay. So again, the best mass spec can measure mass accurately down to, so for to 4 or 5 decimal places. But if you want to measure something's mass that accurately, you need a really expensive instrument to do that. So then you're talking spending $500,000 for an instrument. If you only need to measure the mass to maybe 1 decimal place, so this is going to cost you about $500,000 for an instrument. This is going to cost you about $20,000 for an instrument. So it all depends on how much resolution you need, depending on which instrument you would want. Okay, so let's say a little bit about more what you get from mass spec. So let's say you did them mass spec on chloromethane, then what you would see. So if you just use periodic table and calculate the mass, so carbon 12.011, so if you look on the periodic table, it tells you the mass of carbon is 12.011, hydrogen's 1.007794, and chlorine's 35.453, so 50.4878, right? So if you did the mass spec of chloromethane, then would you expect to see a peak at a mass of 50.4878? And the answer is no, you would not. That's not what your mass spec would look like, right? Why not? So what it would look like instead is you would have a peak at 49.992328 and 51.989378. So 2 peaks. Why 2 peaks? Well, so first of all, you have to keep in mind, if you're looking at a periodic table, so this 12.011, if you remember, is the average atomic mass, right? The average of what? Average of all of the different isotopes in nature. So if you remember, so if we went back up to this neon sample, so this neon, what did we say the mass was? 19.99992. This is 20.994 atomic mass and 21.991 atomic mass. So the average atomic mass of neon is 19.99992 times 0.9051 plus 20.994 times 0.0027 plus 21.991 times 0.0922 to give you the average atomic mass, which that would be 20.1790, and that's the number you find on the periodic table, right? But there is no neon that has a mass of 20.1790. And the same is true for carbon. There is no carbon with a mass of 12.011. That is the average atomic mass of all of the carbon isotopes in nature. So when you're doing mass spectrometry, you have to use the mass of individual isotopes. So let's do this math. So carbon, the main isotope in carbon is carbon 12 in nature, and it has a mass of exactly 12 atomic mass units. The main isotope of hydrogen in nature is hydrogen 1. It has a mass of 1.007825, and there's 3 of them. And chlorine comes as 2 isotopes in nature, chlorine 35, which has a mass of 48.968853. So if you add that up, you get 49.992328. So that peak would be for the CH3 molecule that has a carbon 12 in it, 3 hydrogen 1 isotopes in it, and a chlorine 35 isotope in it. But chlorine also comes as chlorine 37 in nature, so if we added up the mass of that, so 1 carbon 12, 3 hydrogen 1s, and a chlorine 37, so chlorine 37 has a mass of 36.965903, and that would be 51.989378. And so that's where that peak is coming from. So chloromethane in nature is actually some of this molecule and some of that molecule. Which one is there more of in nature, chlorine 35 or chlorine 37? Well, you can tell that by the size of the peaks. This peak is bigger, so there's more chlorine 35 in nature. This peak is smaller, so there's less chlorine 37 in nature. So there is some carbon 13 in nature, but it's only 1.1% in nature. So if you added up the masses with the carbon 13, so this would be with the chlorine 35 and a chlorine 37. So instead of a carbon 12, if you had a carbon 13, then you would see a peak at 50.99. But that peak, since it's only 1% carbon 13 in nature, it's really tiny. And it may be so small that it's lost in the noise in the baseline. And the same would be true if you had a chlorine 37 and a carbon 13 instead in the molecule. Then that would have a mass of 52.99, so about 1 mass unit higher. So there could be a tiny bump here, but again, because there's only 1% carbon in nature, carbon 13 in nature, that peak may be so small that you may not be able to see it out of all of the noise in the baseline. Okay, so chlorine 37 is 24.22% in nature. Chlorine 35 is 75.78% in nature. And if we just take that ratio, it's 0.3196. So when you see this peak for chloromethane, what you see is, so this is often called the M peak, and this is the M+2 peak, 2 mass units higher, because chlorine 37 has about 2 mass units more than chlorine 35. But this peak is about 31 to 32% of the height of this peak. So when you see chlorine in a molecule, it's in a 3-to-1 ratio. The M and the M+2 peaks in a 3-to-1 ratio because there's only about 32%. Well, it's because of this ratio right there, right? Because it's about a 3-to-1 ratio in nature. Okay, so what if you had bromine in a molecule? Well, bromine comes as 2 isotopes in nature. So you can have a bromine 79 in your molecule, or a bromine 81. So if we did the math with H1 and carbon 12, since hydrogen's about 99.9% in nature, and there's only a little bit of hydrogen too, and carbon 12 is about 98.9% in nature. So you don't have to worry about the isotopes of carbons and hydrogens too much in your mass spec, but something like chlorine or bromine you do, because bromine 79 is about 50.69% in nature, and bromine 81 is about 49.31% in nature, so about a 1-to-1 ratio. So if you did the mass spec on this, what you would see is two peaks, one for this molecule and one for that molecule, and they would be in about the same height because the 2 isotopes of bromine are in about a 1-to-1 ratio in nature. This would be at a mass of 93.941813, and this would be at a mass of 95.939766. So it's easy to tell if there's a bromine in your molecule because you have an M and an M+2 peak and a 1-to-1 ratio. So if you have a chlorine in your molecule, you have an M and another peak 2 mass units higher in a 1 or a 3-to-1 ratio. So what if you have a nitrogen in your molecule? So if we had this molecule, for example, So again, if we take the main isotope of hydrogen, the main isotope of carbon, and nitrogen, the main isotope is nitrogen 14. And if you add all of that up, so it's easy to tell if you have nitrogen in the molecule. So only one main isotope of nitrogen in nature. So if you add the mass of this up using the nitrogen 14 isotope, then this molecule would have a mass of 31.042199 atomic mass units. So it's easy to tell nitrogen is in the molecule because the mass is odd. Now, of course, if you have 2 nitrogens, then it's more complex because then the mass is even. 3 nitrogens, then the mass is odd again. But we'll try to keep it somewhat simple for you, and I'll tell you if there's more than 1 nitrogen or not. But so if you see a mass spec and the mass is odd, we can assume there's 1 nitrogen in the molecule, or an odd number of nitrogens. So in organic chemistry, the main elements that you find are carbon, hydrogen, nitrogen, oxygen, chlorine, bromine, fluorine, the halogens, iodine, sometimes phosphorus, sometimes sulfur. And so we looked at how you determine if there's chlorine in the molecule. M and an M plus 2 peak in a 3:1 ratio. Bromine, M and an M plus 2 peak in a 1:1 ratio. Nitrogen, the mass is odd. There's nothing distinguishable about oxygen in the molecule. So for our purposes, though, we're going to basically limit ourselves to looking at the spectroscopy of molecules that just have carbon, nitrogen, hydrogen, oxygen, chlorine, and bromine in them. Just to simplify things a little bit, just so that we can learn the basics of spectroscopy. But that covers a whole lot of organic molecules. So for example, if we took something like zinc, so if we looked at other elements, zinc comes as 5 isotopes in nature. So you have zinc 64, 65, 66, no, not 65. 66, 67, 68, and 70. So this is 48% in nature, 28% in nature, 4% in nature, 19% in nature, and 1% in nature. So if you looked at the mass spec of a compound with zinc in it, so we have a big peak, and then let's try this again. So you have a zinc 64 in the molecule, a zinc 66 possibly in the molecule, maybe a zinc 67 in the molecule, maybe a zinc 68 in the molecule, or maybe a zinc 70 in the molecule. So you would see your peak with your molecule would actually have 5 different possibilities in it. So this is basically like a fingerprint. So mass spec can be a fingerprint for different elements that are in molecules based on what the isotope pattern looks like. Okay, so I think we will stop there. So that's the basics of how a mass spec instrument works, particularly an electron impact mass spectrometer with a mass analyzer, with a magnetic sector mass analyzer. Okay, so we'll stop there, and the next video go into more detail on mass spectrometry.